Good afternoon, everyone. We have 3 more minutes, but let's give Vivek 3 more minutes during his talk. So, yeah. Okay. So through the morning, we've had technologies, computers, smartphones, and screens, and so on. So some of us been part of this movement called the People Science Movements. There's been a very sustained, consistent kind of an interest in materialist things, objects, wood, matchsticks, these kind of things. And Vivek is very much part of the People Science Movements. And Vivek will speak about mathematics now. Thanks.
Start. Okay. We at Navti do a lot of workshops with primary teachers. And let me begin with the first question which I normally begin a workshop with, or the first activity. As all teachers know, there are 2 kinds of people: those who can do mathematics and those who can't do mathematics. So I'm going to show a test by which you can distinguish between those who can do mathematics and those who cannot do mathematics. And this is the test. How many stones in this hand? 2. How many in this hand? 3. How many in this hand? Okay. So everybody who can do this test can become good at mathematics. Second point which we make is that, have I written anything? No. So mathematics is not something which you do with pencil and paper. That's also one way of doing mathematics. What is mathematics? Mathematics is something else. The second point which I'd like to make right at the outset is that we have discussed about math by discovery, learning by doing. The thing about discovery is that you can't do it on a time schedule. Every person has his or her own moment of understanding. And unfortunately here, I have a time schedule. So I'm going to apologize right in the beginning for posing questions and not giving you that extra minute, perhaps, okay, which everybody at some point in time needs that extra minute before you say, aha. But in a lecture like this, it's not possible. So I will apologize to you beforehand on this count. All the things that we will be discussing today are things that we have developed over the years at Navti. Let me spend a minute telling you about Navti. Navti is we call ourselves an SRO. That is a self-reliant organization. Also some other words with that, the self-reliant organization. That means, though we are not a government organization, we are not an NGO, okay, because we don't depend primarily on funding for our activities. For our activities, we depend primarily on income that we generate from our own activities. So we function in a market. So you may call us a social enterprise, but we call ourselves a socialist enterprise. Idea being that this enterprise is not for making profit, but earning a surplus is necessary for the activities. So the main objective is not earning profit, that's a capitalist enterprise. The main objective is the social objectives, for which we earn a surplus, which we invest in our activities. So we call ourselves a socialist enterprise. Now, my colleagues who have been part of this development are here today. One is Vipula Abhyankar, She's a senior resource person with us, and Geeta Mashabde, who is the director of our program, Universal Active Math Program. Okay, let's begin the discussion now. First slide, please. All of you know these things because you're all mathematicians and teachers, so I won't spend time with this. We know that the odd numbers added in sequence give us squares, and we also know that we can make those numbers with these Jodo cubes, and this is the shape of an even number, and an odd number is an even number plus 1. So an even plus an odd number is an odd number, and an even plus an even is even, etc. Okay? The point I want to ask here, I will also raise some questions which I will not answer, but I will ask them anyway, is this a proof of odd numbers added to odd numbers give you even numbers, odd plus even is odd. And if it is not a proof, then why is it not a proof? Okay, why is 2n plus 2m equal to 2m plus n a proof? And why is this not a proof? Some questions which I'll just raise and continue. All of you, of course, know that we can also make square numbers in this shape, 2 square of 2, which is 4, 9, 16. Okay? Next. There is a principle on which we will be working throughout this presentation, which we may call the construction worker's axiom. And that is that all of elementary mathematics can be built up from one simple fundamental principle, and that is that addition is joining. Okay, so if this is 3 and this is 2, then this is, of course, 2 plus 3. Okay. So this is 2 plus 3 if this is 1. But if this is not 1, if this is my 1, then what is this? Half, 1/3. So what is this? Now this is half plus 1/3, right, when this is my 1. So what this is, okay, depends on many things. This plus this is always this. But whether it's 2 plus 3 equal to 5, or half plus 1/3 equal to 5 by 6, or something else, depends on a context. So another point which I would like to make here is that there is hardware, but you can build on the same hardware a lot of different softwares. And on this hardware, you can build software for pre-primary students, you can build software for class 3 and 4 students, you can build software for 8, 9, 10, and you can build software for postgraduate applications. On the same hardware, one can build different softwares. Okay? This could be A plus B, for example. Next. Now, another very important principle is that I can add numbers repeatedly, and that's multiplication. And that means I have to join them repeatedly like this. But instead of joining them like this, I can join them like this. And if I join the same number to itself repeatedly like this, then what shape do I get? A rectangle. So a corollary is that multiplication makes rectangles, and in a rectangle there is a multiplication. That's a very important principle on which we can proceed. Next. Now, this is a division problem. Okay, how many of these fit here? The answer is 2, right? So this divided by this is always 2. But if this is my 1, then what is this? What is this problem? Now it's 2/3 divided by 1/3. right, if this is my 1. And if this is my 1, then it's a different problem. It is 4/3 divided by 2/3. Okay? So what this is depends on a number of things. It could be 2a divided by a. But this divided by this is always 2. Okay? Next. So we know we can make numbers in different shapes, or we can make shapes with different coins. And these are the triangular numbers, which are also the numbers added, the natural numbers added together, 1, 1 plus 2, 1 plus 2 plus 3. Okay? Next. And we all know that we can, the sum of the numbers added in sequence is half n into n plus 1, right? We know that. That can be seen very easily when you put two triangular numbers together, and you get a rectangle in which one side is one more than the other side. So that's n into n plus 1, and since you put 2 together, therefore, it's half n into n plus 1. Next, we have the hexagonal numbers, which I have made there, and they are 1, 7, and then I put another layer of 12, that's 19, another layer of 18, that's 37. And interestingly enough, I assume that most of you know all this, so I won't spend much time discussing this. But if you add them, the first two added together give you cubes, 8, which is a cube. The first 3 added together gives you 27, which is also a cube. And the first 4 give you 64, which is also a cube. So why do the hexagonal numbers added up, okay, give you cubes? Now, this is a proof that the odd numbers, next, added in sequence give you squares. Each of this is an odd number, and you keep adding the layers and you always get the next larger square, right? So this is a proof that the odd numbers give you squares. Can we give proofs like this for the hexagonal numbers adding up to cubes? Again, I won't discuss this, I'll just pose the question. Okay. The point is that all of these are based on the principle that addition is joining. Joining is addition. And we are joining blocks, we're making shapes, and we are reading some mathematics into the shapes that we have made. Next. Now, it's interesting that if you add the cubes, okay, like 1 plus 8, what do you get? 9, which is a square. 1 plus 8 plus 27, what's that? That's 36, which is also a square. So why is it that when you add cubes, you get squares? Now, here's the proof of that. Very similar to the proof that odd numbers give you square numbers. So this is the first cube, this is the second cube. I'll just take the third cube and tell you why it's a cube. Right? And the fourth level has got 5 layers. Okay, each of those 5 squares, and I can keep adding those squares. But interestingly enough, look at what is this. What is it the square of? Okay, it is the square of this line, which is 1 plus 2 plus 3 plus 4, which is a triangular number. So when you add cubes, you get the squares of triangular numbers. Now, there's many more interesting things that we can read into this. But before I do that, we've added natural numbers and got squares. We've added cubes, got squares. Of course, the question arises, what happens when you add squares in sequence? So this is the shape that you get when you add squares, 1 squared plus 2 squared plus 3 squared. I've just taken that. And I've set something up here which I've taken 6 pieces of these here, okay, and I assemble that okay, and I get these 2 pieces which I can then put together and I get a cuboid. I won't do it right now because that takes time and I've got to finish a lot of things. Okay, so remember that was 1 squared plus 2 squared plus 3 squared. I get a cuboid which is 3 on one side, 4 on the other side, and 5 on the other. We can do it in the break. And I took 6 pieces. Okay, so what is 3 times 4 times 5? That's n into n plus 1, but 5 is not n plus 2, it is 2n plus 1. Okay, and since I've taken 6 pieces, I get a 1/6 there. Okay, now the interesting thing is that when I'm added cubes, I'm doing an integration of cubes. So I should get what? I should get a 4th power. Right? When I'm adding squares, I'm integrating squares, so I should get a 3rd power. Sure enough, n into n plus 1 into n plus 1, 3rd power. 2n cubed divided by 6. So that 2n cubed divided by 6, look at the leading term, that's 1/3 n cubed. Okay? So what is that 3 there? That is the dimension. Okay? Now, we've just seen that when I add the numbers in sequence, I get half into n into n plus 1. Leading term is n squared, 2 in the bottom. What is that 2? Dimension. So when I add numbers, I'm integrating a line, I get 2nd dimension, x squared upon 2. When I add cubes, when I add squares, which I just did there, I get n cubed upon 3, 2n cubed upon 6, which is n cubed upon 3. And when I add cubes, I get the squares of the natural numbers. That means I get n squared times n plus 1 squared divided by 4. So that 4 which we see there is the 4th dimension. Okay, and the leading term is n squared times n plus 1 squared, leading term is n 4th. So what we are really seeing here is a 4-dimensional object which has been projected in 2 dimensions. Okay, let's continue. That was sum of squares, 2n cubed upon 6, 1n cubed upon 3. Next. So now we can do a lot of mathematics, understand a lot of mathematics as from addition is joining, because one of the principles that comes out of addition is joining is that you can do space filling. That's what construction workers are doing all the time. Okay, so the tile layer knows how you can fill space with tiles, and we know this one. You can fill a big space, a plus b squared, with 4 tiles, etc., etc. Next. You know, you can tile with equilateral triangles, with squares, with hexagons. Next. But you can also tile with an arbitrary parallelogram. Example on the board. Okay? And you can make a parallelogram out of any triangle just by flipping it over and putting it along one of the sides. Okay? So you take 2 triangles, you can make a parallelogram in different ways. So this tells you that you can tile with triangles, and it doesn't matter how you count, whether you count this way or this way. Ultimately, you fill the room, the same number of tiles. So the area of a triangle is just the area of the room divided by the number of tiles. It doesn't matter whether you're taking this as a base or you're taking that as a base. Okay, next. Just go back, please. Aha. Yeah, skewing the parallelograms doesn't change the number of tiles. Space can be filled with, okay, next. Now, from tiling with arbitrary triangles, we know that all these triangles can be put on a straight line, And at any one point, you can see that the three angles of the triangle join up there. So that's a proof that the angles of a triangle add up to a straight angle, which is 180 degrees. And the other part, which we just discussed earlier, is that the area of the triangle does not depend on what base you take. And that is a very, very non-trivial result. Okay? In fact, most of mathematics, I think, comes out of that one single result. Because whenever you're doing calculations in mathematics, okay, most of the time you are calculating determinants. But what is a determinant? A determinant is really the area of a triangle. And a lot of mathematics, just comes out of that one single formula. So since it's such an important formula, let's prove it. Okay. This is your rectangle, but I can skew that rectangle on this way with this as base. And I can skew that rectangle with this as base. Skewing, shearing has not changed the number of cubes. So it means that this and this have the same area. Okay. Next. Having done this in 2 dimensions, now let's go to the next level of questions, which has to do with 3 dimensions. In fact, most of school geometry, plane geometry, just falls out of space filling in 2 dimensions. Okay, because we proved two theorems. One was the angles of a triangle adding up to 180. Another was about the area of a triangle. The third is right up there on the board, which also in the morning we saw, Pythagoras theorem. All of them have to do with space filling. Okay, a plus b squared can be filled with space, can be filled in 2 different ways, c squared and 4 triangles, and a squared plus b squared and 4 triangles. You remove the triangles, and you have a squared plus b squared into c squared, etc., etc. So most of plane geometry is actually something which comes out of addition is joining and space filling in 2 dimensions. What happens when we go to 3 dimensions? First question we ask is that what kind of bricks will fill space? We know that cuboids fill space. But for example, here I have a tetrahedron, Tetra Pak. Can I fill space with a Tetra Pak? Okay. Next. Having raised these questions, now let me make a slightly stronger statement and a more controversial statement. We'll read it there. Let's define mattermatics as the mathematics that can be understood and discovered by joining matter, that is, by making material structures. Some examples we just saw. But mathematics also has its own structure. We make higher structures out of the lower structures. Both mattermatics and mathematics are assemblies of structures. Okay? So we can ask the question, when can a mathematical structure be represented by a material structure? And a big question, okay, is mathematics equal to mattermatics? Earlier, I had made a weaker statement, which is that all of elementary primary mathematics can be built as mathematics. I will just ask the question now, because I don't want to offend any mathematician sitting here. Is mathematics equal to mathematics? Sometimes, as a statement it may be wrong, but by proving it wrong, we learn a lot of things. So I think it's a useful question to ask. Next. So now let's go to a slightly higher technology of construction, which is what we use today, which is of rods and, not just bricks, but also structures and elements. And this is Jodo. This is a kit that Navti makes. And this is how we earn our bread and butter. There are connectors, and these straws fit into these connectors. And they can take any angle that you give it. Okay, so one can make arbitrary three-dimensional polyhedra using this kit. It's called jodo because in Hindi, jodo means to join. Now, with jodo, we can make shapes. Next, please. These are the 5 regular polyhedra which are made here: tetrahedron, the cube, octahedron, icosahedron, and pentagonal dodecahedron. And I'm sure most of you know a lot about these things, so I won't spend any time discussing that. I'll continue. Next. Actually, these shapes have preoccupied and fascinated scientists and mathematicians from time immemorial. And in fact, Plato and the Pythagoreans were very much intrigued by these shapes. Plato thought that he could explain the structure of matter using these shapes. And he has written a small book on the structure of matter based on a chemistry of faces. Okay? And he tried to explain the properties of those 5 elements, okay, by these 5 structures. The 5th element was ether, something that he called ether. Okay? Otherwise, others were the 4 elements. And he tried to explain their properties using the properties of these shapes. Okay? Next. These are the only structures that can be created if you have all the vertices the same, all the edges equal, and all the faces identical. These are the regular solids. But if you relax the condition, if you say that the vertices have to be the same, edges have to be the same, but faces don't have to be the same. So you can combine a triangle with a square, okay, etc., etc. Then you get what are known as the Archimedean semi-regular solids, which are shown here. So this is like a chemistry of faces, where you combine triangles and squares and pentagons, etc. Okay, now one of those shapes I've made here, this is where you use 4 connectors and you combine triangles with squares. And this is known as a cuboctahedron. Okay, this is one of those. Another one is here, where you've combined triangles with pentagons. Okay? There are 13 of them. Next. Next. The conviction that these shapes had something to do very fundamentally with the structure of matter and the way things are has continued throughout the ages, and Kepler has written a book called Harmonices Mundi. And in that book, earlier he also wrote a book called Cosmographicum. Next. Where he tried to explain the distances of the planets from the sun by the nesting properties of these regular shapes in each other. And he thought that he had the secret of why the solar system was of these sizes. Of course, he was totally wrong. Okay? Had nothing to do with this. But while doing this, he studied lengths of orbits, radii very carefully. And in Harmonices Mundi, not as a main part, but as somewhere at the back of the end of the book, he comes out with his 3rd law relating the period to the radius. Okay? That is where he comes out with his 3rd law, very interestingly. But before that, there's a lot of other very interesting speculation, very interesting thinking. Next. Next. See these shapes here? they were just Plato's shapes. Kepler went ahead. He said, well, the structure of matter has to do with how these different shapes can fit in each other. So he constructed other shapes. These are known as the stellated dodecahedrons. And notice one shape below here, which is the rhombic dodecahedron, which is this shape out here. Okay? I'll discuss this a little more later. Next. He also, as a gift to his, the chap who was funding him, the local ruler, he wrote a book called The Six-Cornered Snowflake. And for that he studied space filling in 3 dimensions. Next. As you can see, he's looked at regular shapes which are formed when you have balls of the same size stacked on each other. And interestingly enough, in this, what he discovered or observed is dead on track. Okay? He was absolutely right in everything that he wrote in this document. And in the same next, he also studied, by the way, beehives. Okay, and he explained why you get the hexagonal pattern in the beehive, and he explained other things. I'll come to that a little later. After that, Descartes discovered a very interesting theorem. Now look at the dates. Okay, Descartes is 1596 to 1650. Go to the next slide, please. Next slide. Euler is 1707 to 1783. So Euler was born after Descartes died. Go back, please. Descartes discovered a very important theorem, which is that the numbers of vertices is related to something that we call the missing angle. Okay? So the missing angle here, this is 108, 108, 108, added up gives you 324. Subtract that from 360. So what do you get? 36. Divide 720 by this number, 36, and the answer is 20. And there are 20 vertices here. Let's apply the same thing here. 90, 90, 90, 270, subtract from 360, 90, divide 720 by 90, 6 vertices of this cube. But not just this cube, everything else that I have here, okay, this one here, all that, okay, obeys Descartes' law. And it's very interesting to build these shapes and then verify Descartes' law. Next, then came Euler, and Euler, of course, gave the famous formula V plus F minus C is equal to 2. Okay? But you can prove Descartes' theorem, and Descartes proves his result by a method which essentially is equivalent to Euler's theorem. So I don't think it should be called like Euler's theorem. It should really be called Descartes' theorem, because Descartes came much before Euler, and he was using this, okay, before Euler did. Anyway, you know what is the Euler index? Next. And now we have an even higher version of all this together, which is what is called the Gauss-Bonnet theorem, okay, which says that if you integrate the curvature over a manifold, then the integrated curvature is equal to the Euler index times 2 pi. So why do you get 720? Because that's 2 times 2 pi. 2 pi is the 720. 2 times 2 pi, and 2 is the Euler index of the sphere. That's also the Euler index of any of these shapes which are topologically equivalent to the sphere. Okay, so it's very interesting to add up V plus F plus minus E and see that it is true for all these shapes here. Okay, so some very interesting exercises for children which are very low-hanging fruit. Okay, all these angles can be measured, Descartes' theorem can be verified, and interestingly enough, you can make an arbitrary shape, not a regular shape, add up all the angles. Okay, so we add up all the angles, add up the missing angle, and it turns out to be just Euler index times 2 pi. Angles don't have to be all the same, vertices don't have to be the same. So some very interesting applications of these shapes to mathematics, which is done at the MSc, at the graduate or postgraduate level. Okay. Next. Some interesting questions are posed. Very interesting poses arise. One poser, historical poser I mentioned earlier, which is that why do we call it Euler's theorem when Descartes, who came much earlier, used it to prove his result, which is a much more interesting and stronger result. Another very interesting poser has to do with something we call Catalan solids. Okay? And that has to do with something called duality, which is another beautiful idea which is great fun with kids. Now you see, if I take this shape here, this has 6 faces and 8 vertices. Now I interchange vertices and faces. Okay? This vertex is, let me call it a 3 vertex. And let me call this face a 4 face. Okay? Why? Obvious. Now I interchange vertices and faces. So now I will look at 4 vertices and 3 faces. So I make a shape using 4 vertices and 3 faces. That means I make a shape with triangles using 4-way connectors. We've done it already. That's just this. Okay, so the cube and the octahedron are dual to each other. Okay? The same applies to the dodecahedron and the icosahedron. These are dual to each other. Now the question comes, why don't we apply it to this? Okay, before that, what about the tetrahedron? 3 vertices and 3 faces, you interchange them, you just get 3 vertices and 3 faces, so it is self-dual. Okay? Nothing happens, it just comes back to itself. But then what happens if you apply duality to the semi-regular polyhedra? Why did the Greeks not apply duality to the semi-regular polyhedra? Because it's such an obvious concept. And in fact, I hit upon this before I read about all this stuff. But the duals to the semi-regular polyhedra are associated with the name of a mathematician called Catalan. Okay, so let's go next, which is 1865. Why did it take all those years to make the Catalan solids? Okay, because the Greeks knew the rhombic dodecahedron, and that's the one which is dual to the cuboctahedron. But why did they not also try to construct the duals of the other Archimedean semi-regular polyhedra? My hunch is that they did, and that's a lost book. Okay, because they did so many things, they couldn't have missed this. So we call it Catalan solids only because that book somehow is missing, because it's got lost, but the Greeks must have known about this. It's such a obvious concept, okay? But when you do construct the duals, I have constructed, this was one of the Archimedean semi-regular solids, and it's very interesting to look at this and start constructing the dual, very simple exercise, and this is what you get. Okay, because all the connectors here are 4-way connectors, so everything here is a 4-face, but here the 4-face is no longer a square, now it is a rhombus. Okay, and here you have 5 faces and 3 faces, that is pentagons and triangles. So what you have here is some 5-way connectors and 3-way connectors. You just follow this and this makes itself. A very interesting exercise to construct duals to all the shapes that we made earlier. Next. These are some others. This is the Archimedean semi-regular solid, and what we have on this side is the Catalan dual. Next. So now let's take the discussion a step further, and let's look at science. Now, our modern understanding of science is an understanding based on the structure of matter. At least that's a large part of our modern understanding of science. Okay? The very fundamental principle that the function of some material structure depends on the structure. So in some ways, function is determined by structure, and structure is also shaped by function, because that's what the theory of evolution is all about. Okay, that by certain functions, certain shapes get selected. Okay, so the relationship between structure and function is very direct and deep. So we could say that science is largely the architecture of matter. And let's just take a glimpse of that, a bird's eye view of that. Okay, next. So now let's look at mathematics as physics. Okay. Crystals arise out of space filling in 3 dimensions. They are structures which fill space in 3 dimensions. So diamonds are an example of that. We'll discuss this a little later. Next. Carborundum is silicon carbide. Okay, so it's diamond structure, but every alternate molecule is replaced by, carbon is replaced by silicon. Carbon has valency 4, silicon also has valency 4. That's why it can happen. We know that diamond is very hard, so we would expect that silicon carbide also would have a similar property. And indeed, silicon carbide is otherwise known as carborundum, which is the second hardest most. Okay, diamond is the hardest substance known to us, and carborundum is the second hardest. And it arises out of the structure, all the 4 bonds locking up with each other in very tight manner. That's what gives it its hardness. And so we see structure-function relationship right there. Next. We have C60, another way of joining carbon. Well, Smalley got the Nobel Prize in 1996 for that structure, but that structure was really constructed first by Archimedes. It's part of the Archimedean semi-regular solids. Okay? And before Archimedes, there are many cultures which also knew this, okay, this shape and used this shape. Next. Now we go up, zoom up a little bit, and we come not from the nano world, we come up to the level of viruses, molecules, and it's interesting that most viruses have a structure which is polyhedral. Okay, this is the polio virus. Next. That is a herpes simplex virus. This is the adenovirus, which is close to the virus which gives you a common cold. Okay. Next. We zoom up a little bit. We come to pollen particles, which also are in this polyhedral shape. And similarly, in the sea, next, there are the radiolaria, which are, again, very much in these shapes. Okay. So if you make these shapes with Jodo, there's one thing about it is that, in a way, you don't have to, you start making it and then you don't have to think. The shape makes itself. Okay. So the prevalence of these structures at various levels of the natural world must have to do with this property, that these shapes have a tendency to make themselves. Okay. Next. Next. So let's zoom up a little bit and come to structures which we can hold in our hands. Where do bees learn geometry? Okay. And now this was what Kepler had studied, and this is what Kepler writes in his book. He says that this is that structure of the bee's hive. What you have here is bees who are all the same sized, and when they start making their hive, they all come to each other and they start secreting the wax. And they want to do it, and they push against each other, and then what happens is that they get into a close packed configuration. And here, what you have here, where they are joined to each other, is close packing. Okay? And that close packing is something which, when they push against each other, they flatten that wax, and what gets constructed is this rhombic dodecahedron. I've got a set of balls out here, okay, made out of Play-Doh, which are close packed, and sometime after the lecture we'll sit down and we'll compress it and we'll open it up and see what happens. But what happens when you do it, okay, most of the time, is that you get these rhombic dodecahedra. Okay, so the rhombic dodecahedra arise out of the close packing, and that's one of those shapes which close packs. Cubes close pack, tetrahedra don't, but rhombic dodecahedra close pack. And the bees, okay, this is the rhombic dodecahedra which are close packed. And I've changed the color, okay, of some of the straws, and you can see a bonding structure if you look at the blue straws. And this bonding structure is just the structure of diamond. Okay, so this is the blue straws are the diamond crystal. So diamond also arises out of close packing of the rhombic dodecahedra, just as the bee's hive arises out of close packing. And if you take this rhombic dodecahedra, and I cut out this piece here, because the bees, after building the cells, the bees have to come out. So they do the close packing here, and then they start coming out, secreting. That's when this part gets constructed. And finally, they emerge here. And this hexagon that we see here is just this hexagon here. Okay? So it is really a kind of an elongated rhombic dodecahedron that is then cut off where the bees emerge. And that's where this hexagonal structure comes out of. So we could say next, and this is something that Kepler wrote about, okay, in his 6-cornered snowflake document. Next. So where do the bees learn geometry? So Kepler and the bricklayer give the same answer. You can build thick walls with rhombic dodecahedra because you can fill space with rhombic dodecahedra. So bees and diamonds are the alumni of the same school. Okay. Next. So now let me wind up by looking at a number of space-filling toys. Of course, we have these here, which we played with earlier. We have Jodo, which we just played with for the last 20 minutes. There's this lovely little toy called the Pharaoh's Pyramid. Okay, this is a stacking toy, which has a lot of very interesting properties. One property is you can take this, and it's very easy to calculate the Euler index of this. Okay, just by adding sides v plus f minus e. When you do it, you don't get 0, you get minus 2. Okay, and then you can apply, you get 0 for this, 0, not minus 2. Okay, for the sphere you get 2, for this you get 2 minus 2, which is 0. So this would mean that the sum of the missing angle, which you can also do here, you can do the Descartes sum, it should be 0. and in fact it is 0. So you can make various shapes. Here I've made the same structures. This one here has been made with Jodo. And we see what this is. What this is really is a combination of the green straws are the octahedra and the red straws are the tetrahedra. So it's a property that the octahedra share with the tetrahedra, and they don't fill space by themselves. Neither this nor this fills space by itself, but the combination of octahedra and tetrahedra fills space. So this straw here is based on the property of octahedra and tetrahedra to fill space. All the questions that we asked earlier about these shapes can be asked about this. It's very interesting, and if you want to get really challenged, calculate the Euler index of this. Okay, very interesting problems, non-trivial problems. Okay, so doing Descartes, doing Euler is an extremely fascinating exercise. And by the way, this is also why the hexagonal numbers added in sequence. Why is it that they give cubes? This also answers that question, but I won't get into that right now. Okay. So next. Now we zoom up to structures bigger than us, and we get into real architecture. Next. Geodesic domes. Next. So now let's take the final point, which is that there are material structures. Mathematics is also an assembly of structures, but understanding is also an assembly of structures. Pedagogy and understanding is something which is a set of higher and higher structures, a sequence of concept constructions. Next. What's going on in a child's mind when you're doing mathematics is an open question. But clearly it's not what's going on in your mind. Okay? But certainly what's happening in that child's mind is very interesting. And while using these materials creatively, we are creating a lot of very rich structure in the child's mind, which is what education is all about. This is my grandson, who was very interested in there's a festival in celebrated Maharashtra, which is known as Govinda, where human chains are formed, human pyramids are formed. So while I was playing blocks with him, he was playing what he was really interested in. Yeah. Next. So there is a broader issue of constructing math understanding, and probably a very powerful principle there, which we may paraphrase Descartes, okay, who said, "I think, therefore I am." We may paraphrase him and say, "I do, therefore I think." Next. And that is important if we are trying to construct not just structures in the minds of one child, but understanding at a mass level. We are trying to construct universalization of quality math education, universalization of quality science education. So learning by understanding, if we want to do that, math for universalization must be popular, and there has to be understanding by playing, doing, making, constructing, which is what kids enjoy doing. Next. So can we conceive of a big repertoire of such activities, okay, which kids will enjoy, with equipment that they make themselves, experiments that they do with stuff that they make themselves, where every activity is a wow activity, which then leads up to the question of why and how. Okay. Can that be done systematically at every level from primary to high school and beyond. Next. So can we construct a mass math and science understanding? We believe that it is possible, and that's really something which requires a thought about the systems. It's something that we have to do right now with our Right to Education Act. Next. Thank you.
So, how do you think we can try to explain probability or statistics using Jodo? It's a part of mathematics, right? So,
may not be Jodo, but I can do it with stones, with which I started with. Okay, this is a very good way to begin discussion of probability and statistics. Okay, you can do a lot of combinatorics just with stones and katoris, and then you can ask many questions. You can do a lot of experiments with dice. Okay, so material structures, not necessarily Jodo.
I mean, the entire thing is about matter and structure of matter that you're building, but I didn't see the continuum anywhere.
You didn't see?
The continuum anywhere. So, using discrete structures, using discrete objects. So I mean, this is a question, and
yes.
there's another side I want to mention. You know, Arnold, the mathematician V.I. Arnold, he says mathematics should be taught only through physics, and he has, you know, consistently written about it and argued about it, and he's totally anti-Bourbaki style. But then, of course, you know, for him the continuum, real analysis is sort of central to the whole way of thinking about mathematics. So, you know, there is a lot of parallel in, you know, this idea of taking matter as the central way of thinking about mathematics, but I don't see the continuum. So that's my question.
Okay, I won't answer the question, but I'll just react to that by saying that the continuum is something that you and I think about. It's something that happens in our brain. The brain is something that is made out of matter. That's made out of atoms which are discrete. So if a structure which is made out of discrete matter can make a mental construct of the continuum, then the gap between discreteness and continuity may not be that unbridgeable. But I will just make that comment here, and yeah. I was being provocative, of course, but
yeah, the materials are wonderful. So do you think once someone, you know, takes the material, you need to give them training of how to use it, or it is self?
It's not self-explanatory. Okay, the kind of software that you build on any one of these pieces of hardware, okay, depends a lot on you know, the context, but it's something that you know, is available. We have a website, I think it's there, right? navtinvrithilearning.org. So there are some manuals, and there's a lot of stuff available on other sites, and but it's something which requires some study and teacher training, and it's not something that happens by itself. No.
Anyone else? Okay, thank you, Vivek, and to the Navtinvrithi team. Thanks for that.